Hello everyone, my name is Marzieh Savadkoohi and I'm a PhD student in engineering and computer science. I'm working in the Center of Nanotechnology and Education CNRE lab under supervision of Dr. Tyagi. I'm going to present the results of my research, which is about studying magnetic tunnel junction-based molecular spintronic devices, which is abbreviatedly known as MTJMSD devices, and using Monte Carlo simulation. So the results that I'm presenting today is what I have done during the fall semester until now. So I'm going to go through a brief introduction and the motivation for this study. Then I will briefly talk about the theory and the methodology, the results we have got so far, and the conclusion of future work. So let's see what is a MTJMSD actually abbreviation. What does it mean? Magnetic tunnel junction molecular spintronic devices are the multi-layer shaped structures which are composed of two layers of ferromagnets, as we see here in the A panel of the figure. There are two ferromagnetic material which are basically here in this example made of nickel iron cobalt and nickel iron on top of each other. And also there is a thin layer, a nanoscale thin layer of insulator aluminum oxide between these two layers. So these insulators are called tunneling barrier, and if the voltage is applied, the electrons can actually travel from one electrode to another electrode. But if we want to take the advantage of the spin of electrons, and if we want to create the spin channels, then we can connect these two electrodes through the molecular bridges. So the molecular bridges that are connected to these two electrodes, they are themselves composed of different sections. There is a magnetic core, there are tether links, and also anchoring groups. So this combination of molecules can make connections between these two electrodes, and then the conduction or the current would be happening through these actually molecular bridges. And with this method, we can utilize the spin property of electron. So using the spin property of electron would lead us to have like wide range of novel phenomena and also device mechanisms. So why are we doing this research, and what is the motivation behind this research? So molecular spintronic devices, or MTJMSD device, actually are potential candidate for futuristic computers and advanced memory devices, and they have application in the computational technologies, especially quantum computing. And they can increase the power, they can actually consume less power, significantly less power, but they can lead to the next generation of memory and computational devices. They can increase the speed of the processing and the data processing and information processing. So in the conventional computers, as we are aware, the calculation is based on a binary system. So the computational unit is a bit, which is either 0 or 1. So it's like a switch that can be on or off. Based on this system, the data, which is the information which is given to the computer, it's to be processed. Actually, it finds the right answer one by one, and it uses the binary system to analyze the information. So it takes a lot of time, or it can be time consuming for very, very complex problems. But in comparison to the conventional computers, the quantum computers, they use another computational unit, which is called qubit or quantum bit. Qubit can be either on the 0 state, 1 state, or the superposition of these two states. So instead of having only 2 states, we can have 0, 1, and the superposition of these 2 states. So in that case, we can have a much faster processing, information processing speed, because it considers many different possibilities at once, and it goes through sets of probable outcomes and converge the answers to find the right and the correct answer. So if you want to see a little bit about the physics behind the qubits, which is a unit in the quantum computing, uses the spin of atoms. So what we mentioned about making the magnetic tunnel junction spintronic devices is because of what we are explaining here. So they uses the spin of atom, and the spin of atom can be either on the 0 state or 1 state. So in physics, when the electron is in the ground state, the spin can be in the 0 state, and when the electron is excited and goes to the excited state, the spin state can be 1. So the probability of the outcome for the 0 state is alpha squared, and the probability for the state 1 is beta squared. So finally, the sum total, the square of alpha squared plus beta squared is 1. And any combination of alpha squared plus beta squared that gives us 1, any spin state that can satisfy this equation can be considered as a state, or can be considered as a spin vector. So as we see here in these figures, the spin can be up or at, it can be up or at any other direction, and the sum total or superposition of all these cases can give us a lot more different probabilities than having only 2, 0, and 1 cases. So when we actually work with these MTJ devices or MTJMSD devices, we have different factors and elements that contribute to the final product. We can have different kinds of metals, ferromagnetic metals, or the molecules that are used as the bridging molecules. They can made of a lot of different kinds of elements. So these all factors can affect the total device behavior and the magnetic device behavior. But along with the material that are used for making this device, there are other elements like the device size, the molecule's positions, the dimension of the molecular plane, the temperature at which the study is conducted, and the magnetic field, if it is applied or not, the spin of the electrodes and the molecules, if we consider the free electrons or not, and also interatomic and intraatomic Heisenberg exchange couplings between different layers, atoms of the layers, and also between the molecules and the electrodes, and also anisotropy and biquadratic couplings. So there are, as we see, a lot of parameters that can be used to define and design these devices. But obviously, it is extremely challenging to investigate all these possible cases experimentally, because we would have wide range of possibilities and magnetic behavior. So in this figure, you see that we have 2 electrodes in a magnetic tunnel junction material and device, and the first panel is a bare device which hasn't been treated by the molecules yet. But after it is treated by the molecule, we have actually very obvious difference in the device behavior, the magnetic device behavior, which is these images are taken by the magnetic force microscopy, and we can see that when the molecules are attached, we can see a different behavior in the magnetic properties of device. So to see what kind of differences, what kind of behaviors we have, before the experimental work is started, we started to do our study with the simulations to consider all different cases, all different scenarios, and different parameters. So Monte Carlo simulation has been used to encompass a large variety of possible MSDs, magnetic molecular spintronic devices, and we actually expect that the result of this simulation help us to consider many different kind of possibilities in the real world and to design the real device experimentally. So the Monte Carlo simulation in this study uses the Metropolis algorithm, and let me explain a little bit about the images that we have here. So here we have the image on the right side shows the icing model of the magnetic tunnel junction molecular spintronic device. So here we have 2 layers of ferromagnetic electrode on the top and bottom, and we have 1 layer of molecules between these 2. So these molecules have connections and interactions with the electrodes. And the interactions between these molecules and the electrodes is defined by a variable which is called Heisenberg exchange coupling. So the interaction with the top electrode is JML, and the interaction with the bottom electrode is JMR. But the reason that we have put L and R is that in our final simulation, the electrodes are left and right instead of top and bottom. So JML and JMR is the interaction between the molecule and the right electrode and molecules on with the left electrodes. But along with this Heisenberg exchange, which is atomic exchange coupling between the atoms and the molecules, we have interatomic couplings also between the atoms of one electrode. So this is the interaction, the Heisenberg exchange coupling for the atoms of the right or the top electrode, and here it is for the left or the bottom electrode. So this is one result of our simulation. The molecular plane has been defined between two layers of ferromagnet, and the device size is 50 by 11 by 50 by 50, which means we have 11 layer depth, 5 layers of ferromagnet on the left, 5 layers of ferromagnet on the right, and the molecule has been located exactly in the middle between 5 layers of each ferromagnet. So the goal for this study is when we do this Metropolis algorithm, we are going to minimize the energy of the system, because the system always tends to go to the equilibrium state, or to the state to stabilize. So the equation that is used to calculate the energy is shown here. So we have this Heisenberg exchange coupling, JL, JR, JML, JMR, and also we have the product of spin vectors of the molecule and the atoms. And totally we need, and when we do the experiment, when we do the simulation, we need to see that the energy is minimized, and we can see that during the time, the energy is going to the lowest level. So as was mentioned, there are a lot of different scenarios and factors that can be used and varied to change the change the device behavior and to investigate the device behavior. But in this study, I'm working with two different parameters, which are JML and JMR, and we're going to investigate the effect of nature of couplings and the strengths of couplings. So with the nature of couplings, we have considered 3 different cases when molecules create ferromagnetic couplings with the electrodes, when molecules create antiferromagnetic couplings with the electrodes, and ferromagnetic couplings with one electrode and antiferro with another electrode. And also we have changed the strengths of these couplings. So here we have the values that has been used for JML and JMR. The JML and JMR are changing between -1 to 1 with the step of 0.2. And for each value of JML, we have 11 corresponding value of JMR. So totally we have 121 data set produced out of this experiment. But we have also 3 repetition to validate the results and make sure that the results are consistent. We do 3 repetition for each simulation. So I would finally come up with something more than 300 data set for just investigating the effect of molecular couplings. When we do simulation, we have to keep other parameters constant. So we have the simulation count, frequency, molecular position, temperature. And the simulation count can be different based on the temperature we are using and maybe other parameters. But here we observe that this equilibrium state can be achieved by 200 million simulation. And the frequency at which the data is recorded is 50,000. As we said, molecule is in the 5-5 position between 5 layers of the ferromagnets, and KT is 0.1 of the Curie temperature. And we have also combination of 11 values of JML and JMR. So after doing the simulation and recording data, we started analyzing the data. So here I'm going to explain the temporal evolution of the magnetic moment of the MTJMSD device. So as we see here in this graph, in all these four plots, the x-axis shows the count or the simulation count, which represent the time, and the vertical axis is magnetization. So we are showing the temporal evolution or the time dependence of the magnetization. And as I said, there are 121 different cases that could be represented here, but I'm just focusing on the four extreme cases. So let's suppose that there is no coupling between the molecule and the electrode. So JML and JMR are equal to both 1. So we know that each electrode is composed of 1,250 atoms. So the maximum magnetization that each electrode can attain is 1,250. And totally the whole device can be about 2,500 magnetization, the magnetic moment magnitude. So when we have no coupling between the left and right electrode with the molecule and the electrodes are kind of independent of each other. So we see the total device magnetization and the electrodes have a certain number, but we can compare this with other cases where we change the couplings rates. And we have hypothesized that by increasing the magnetic couplings between the molecules and the electrodes, we can see a very significant change in the device behavior in terms of magnetization. So when we have JML, a negative or antiferromagnetic coupling with one electrode and ferromagnetic coupling with another electrode, we see that the left and right electrode magnetization during the time cancel out each other, and we see the total device magnetization approaches 0. So the total device magnetic moment is nullified when we have antiferromagnetic coupling on one side and ferromagnetic on the other side. When it goes to antiferromagnetic coupling of the molecule with both electrodes, when both are -1 and -1, we see that the effect of magnetization of these electrodes enhance each other and improve the total device magnetization. And the total device magnetic moment approaches the maximum number, which is 2,500. And the same case happens when we have 1-on-1, when we have ferromagnetic coupling on both sides of the electrode with respect to the molecule. So this result tells us the number of molecules we have used in this simulation, which is only 16 molecules, is capable of affecting the whole device behavior, and they can control the electrode. They can force the electrodes to take the spin orientation parallel or anti-parallel with respect to each other. And putting those molecular bridges are highly influential in terms of defining the device behavior. So we observed the temporal evolution of magnetization of the device. Now we want to see what is actually the spatial distribution of the magnetic moment. So the magnetic moment can be recorded in 3 different directions of x, y, and z. So again, we have 4 extreme cases of 0, 0, -1 and 1, -1, -1, 1 and 1. And we can see that the stabilization or equilibrium can happen either in the x direction or y direction and z direction. And since this is totally a random process, in each repetition, we can see this magnetization happens in a different direction, but that is not that's not a problem, because we just look for the equilibrium state. So when we have a 0, 0 case, the total device behavior and the spatial distribution of the magnetic moment can be observed here in the x, y, and z direction. And when we look at the y direction, we see that the molecule spin takes multiple colors, which means that there is no connection. Because there is no connection between the molecule and the electrodes, the molecule is totally independent and behave totally independently and takes different colors, takes different spin states. And since we have defined JL and JR as a constant in our simulation, we have same colors for the electrodes, which shows that both of them are ferromagnetic electrodes. When we go to the next step, -1 and 1, we see that the equilibrium happens in the x direction. So on one side, we have like a solid blue, and on the other side we have yellow. And we expect to see antiferromagnetic coupling of the molecule with respect to the electrodes, which is totally observable here. The molecule has ferromagnetic coupling or the same color with respect to one electrode and antiferromagnetic coupling with the other electrode. So not only the molecules force the electrodes to take a special spin orientation, the molecules themselves also have the spin orientation very coherently, and the correlation between them is very strong. When we go to the next case, -1 and -1, we see that the coupling has been able, the molecular coupling or the molecular induced coupling has been successful to create antiferromagnetic coupling of two electrodes with respect to the molecule. Again, the molecule has a strong correlation, and the spin orientation for the molecule with respect to the, and also the spin orientation of the electrodes are coherent and correlated. And in the 1-1 case, when we have ferromagnetic coupling of the molecule with the electrode, we see that all of them taking the same color, which means that the molecule has induced ferromagnetic couplings on the two electrodes, and it has also a strong correlation with the electrodes. So each of these cases can give us a different magnetic behavior of the device that is designed. So again, as was mentioned before, this is the result of an experimental work, and this is a bare magnetic tunnel junction without molecules, but after the molecules are attached, the device tends to take actually antiparallel or antiferromagnetic coupling, which is kind of equivalent to this case that we have here, -1 and 1. So these results kind of confirm the previous experimental results done by Dr. Tyagi and his team. So we have also the autocorrelation contour plots. So when we look at these lattice plots, we cannot see numerically how these spins or how the magnetic moments of the spins are correlated. But with the help of autocorrelation contour plot, we can observe it clearly. So in these plots, we have representation of the device along the width and the depth. So the depth of device is 11 layers. We have 5 layers of the electrodes on the left, 5 layers on the right, and we have the molecular layer between. And the width of the electrode, for each electrode, we have 50 atoms. Each electrode is 50 atomic long. So to calculate the autocorrelation between the spin of molecules and the atoms, we have calculated the correlation coefficient, which is the dot product of a spin of molecules and spin of average of each 5 atoms, because we have 50 atoms, and each 50 atoms, and in each actually electrode we have 5 atoms in each actually row. So we take the average of each 5 atom, and it is multiplied by the spin of the molecule. So in the 0-0 case, there is no correlation exists between the FM electrodes and the molecular spin. So the average color is about like 0 all over the device. But when it comes to the -1 and 1, we obviously see that the molecule has ferromagnetic coupling or parallel coupling with one electrode. And it is like the average is maximum, it's about 1, and antiferromagnetic coupling with the other electrode. So which is the whole, the average of whole value is about -1. And also we see that along the cross junction, we have, actually these circles have been moved for some reason, but across, exactly at the cross junction, we have a strong correlation. For -1 and 1, we have antiferromagnetic coupling of the electrode with respect, of the molecule with respect to the electrodes. So we see that the correlation value for the molecule is shown by a yellow color on the order of 1, but it has a negative or opposite correlation with respect to the electrodes, because this is antiferromagnetic couplings on both sides. And in the last case, the molecule can make ferromagnetic coupling with respect to both electrodes. Again, this circle should be higher, and it shows that at the cross junction we have a stronger correlation. So the nature of molecular couplings that we are changing here in this simulation actually influences the spatial correlation states of the spins of the whole device behavior. So what I explained just in the last slide can be also observed here in 2 dimensions. So in the 0,0 case, there is almost no correlation between molecule and the layers. In the -1 and 1 case, the correlation is positive on one side and negative on the other side. In the 1,1 case, when we have both ferromagnetic couplings of molecule and the electrode, we have all positive correlation with both sides. In the -1 and -1 case, molecule has totally opposite correlation with 2 electrodes. Also, we have the contour plot for the whole device and also molecule, left electrode and right electrode magnetization for a wide range of JML and JMR values. So this is like a comprehensive picture of device behavior when we apply and when we have all these JML and JMR values at once. So we see that generally the total device magnetization is determined from the sum total of magnetic moment of the left electrode, right electrode, and the molecule. So wherever we have both negative values, like negative here, or positive here, positive JMR, positive JML, we have a high magnetic moment. And wherever we have antiferromagnetic coupling, negative values on JMR, positive value of JML, or reversely, positive of JMR, negative of JML, we have low magnetic moment. And there is a transition between low to high magnetic moment. So when we look at this graph, we see that this transition happens somewhere about 0.2, but we need to look at this transition point more precisely. That will be explained later. For the molecule, we see that averagely molecule has a strong correlation with the electrode. So we have like a high magnetic moment almost for all range of values. But in the center, when JML and JMR are 0 or very small values, then the magnetic moment of the molecule is about 0. And the magnetic moment of the left and right electrode, almost all over the range of JML and JMR values, is between 1,000 to 1,100. And we mentioned previously that the total magnetic moment of each electrode is 1,250 magnitude. So in order to find the precise transition point from low to high energy, or reversely from high to low, we have illustrated the magnetic moment versus JMR in 2 dimensions, and we have drawn that for different JML values. So again, we see that when JML is 0 and there is no coupling on the left electrode, the total device magnetization is kind of independent, and no transition can be expected here. But when we increase the couplings, the molecular coupling on the left electrode with respect to the JMR, we have transition from low energy to high energy somewhere between 0.1 to 0. To define a detailed value, we have focused on a strong case when JML is equal to 1, JMR is between 0.6 to 0. And we have drawn M versus JMR. So we see that the transition happens somewhere 0.3 to 0.2. So this tells us that transition point happens at around 20% of the Curie temperature. And we can still go further and find maybe a more precise value for that. So we still confine the range, the JMR range, between -0.3 to 0.3 and the step of 0.05. And we did the simulation 3 repetition for that. So we have the evolution of magnetization versus JMR. And in order to find exactly where the transition happens, we have calculated the first derivative of the plots on the first row, and the second row shows the derivative. So after calculating this derivative, we see that this first peaks happens somewhere around 0.15. So this is consistently can be seen in 0.15 or 0.2 in other cases, in other repetitions. So finally, we decided that the transition point is consistently about 0.1 plus minus a standard deviation, which is 0.05. And here we have a JML value of equal to 1, and this has created antiferromagnetic coupling with respect to the molecule has created antiferromagnetic coupling with 1 electrode. And it shows that when the coupling strength is only 15% of the Curie temperature or higher, a large area of the electrodes can be affected, and we can see the effect of the molecular coupling and the induced molecular coupling magnetic behavior on the whole device. Another feature that has been investigated is the magnetic susceptibility of the device, again for the main 4 cases. In the 0,0 case, when there is no communication between these electrodes through these molecules, we see that the magnetic susceptibility of the electrodes is very low, but the magnetic susceptibility of the molecule is very high. In other cases, when we have these connections, the magnetic susceptibility is averagely the same in the electrodes. But in this case, when we have -1 and 1 case, even the molecule has the same range of magnetic susceptibility. And in the -1 and -1 case and 1 and 1 case, which is both ferromagnetic and both antiferromagnetic coupling, the molecule has a stronger magnetic susceptibility compared to the electrodes. And when we have, if we apply the external magnetic field, the switching phenomenon can happen either when we have a very weak coupling, molecular coupling, or when we have both antiferromagnetic or ferromagnetic coupling. But when that susceptibility is kind of uniform all over the device, then the switching phenomenon could be challenging. So in conclusion, our Monte Carlo simulation showed that the molecular coupling, the nature of molecular coupling and the strength of that can define the total device behavior and can actually affect the interaction between the electrodes and their spin orientation. So when we have parallel or similar ferromagnetic couplings, we have the maximum magnetization. When we have antiferromagnetic coupling, we have minimum device magnetization. Our study shows that when the strength of JML or JMR is about 15% of the ferromagnetic electrode's Curie temperature, only 16 molecules that were used in this simulation can affect a total device behavior, which is composed of 2,500 atoms above the room temperature. And molecule-induced coupling effect is stronger near junction areas, and magnetic field-induced switching, when we investigate the magnetic susceptibility, the switching phenomenon can be expected when there is a very low JMR or when both are positive or both negative. And combining molecular magnetism with ferromagnets can actually create a platform for highly correlated systems. So in the future, we are going to continue this study. I'm going to investigate the effect of different temperatures on the device behavior, the effect of different sizes. So we are going to see how far we can go with increasing the device size, and how we can see if how much we can see the molecule can still affect the total device behavior. Also, we will investigate another feature, which is a spin fluctuation and different intensities of that, and a very exciting part, which is the experimental part and device fabrication. So what I have presented here has been submitted to the Journal of Magnetism and Magnetic Materials, and to the abstract also has been sent to 2 conferences, MRS and APS. We got the good news of APS acceptance last week, and we are all very glad for that. But we are still stay tuned for the results of the journal and also MRS. So at the end, I want to acknowledge my advisor, Dr. Tiagi, for giving me the opportunity of joining his team and for his great support and great mentorship. I want to appreciate all my teammates and my friends, which are kind of, after a few months, they're like my family members. And special thanks to Chris and Andrew, who did like amazing job to analyze data and create the platforms we needed for this simulation. Also, I wanted to acknowledge the funding sources: National Science Foundation, CREST Award, and Department of Energy, National Nuclear Security Agency.